Hello. It's, yeah, now only. Okay, so guys, can you hear me?
Yes, sir.
Hello.
Yes, sir.
Okay. Yeah, so we'll be continuing this chapter, heat and thermodynamics. We did half of it yesterday. You can just start from this. You can write other chapters later. Yeah, okay. So today we'll be doing the laws of thermodynamics. So there are three laws. Okay. So the first law, this one's very simple. I already explained in the previous class. So just take it down. The first law of thermodynamics states that the first law of thermodynamics states that energy cannot be created nor destroyed. The first law of thermodynamics states that energy cannot be created nor destroyed. Full stop. It can only change. It can only change form. It can change form or be transferred from one object to another. It can only be changed. It can only change form or be transferred from one object to another. Okay, so there are few people who are new here, so I'll explain this again. I mean, the similar thing was already explained in the past. Anyway, um, so yeah, listen up. So there are various types of energy. There's wind energy, chemical energy, and everything. The in the universe, you cannot create energy out of nothing. There has to be some form of energy which exists, which we can use. Are you getting me? So, for example, when we burn coal, you are converting the matter into energy. Matter and energy are interchangeable. So, you are converting chemical energy to heat energy. And from that heat, you can convert it to, like through steam, you can convert to mechanical for a train, for example. Or from, steam, you can even make electricity. And they use coal to make electricity. So it can be converted from one state to another. That's all. You can't destroy energy, you can't create energy out of nothing. That's all. Simple. Okay. That is the first law of thermodynamics. So the second one, okay, let's take this down. Second law of thermodynamics. The second law of thermodynamics states that the second law of thermodynamics states that the entropy, ENTROPY, states that the entropy in an isolated system, the entropy in an isolated system always increases. The entropy in an isolated system always increases. Okay. So what is entropy? Entropy means the state of chaos, of in the universe. Okay? So the thing is, when we started, when the universe started, it was small. We don't know exactly what it was. But basically, it exploded, and because of the Big Bang, the universe was created. From that time, the universe, the state of the universe, and everything in it is getting worse and worse, meaning getting more unstable. Are you getting me? That is what this law says. The easiest way to understand is like imagine your room. You clean it up. Over time, it will just get dirty. Even if you don't do much, it just ends up getting dirty, correct? So in universe is the same thing. Eventually, every single matter, the universe is expanding, the matter is expanding, everything, and the state of it is getting more and more chaotic. This is what second law says. That's all. Am I clear? You're taking some notes? Okay, just take it down. So entropy, I'll give the definition of entropy. Okay, this is the meaning. Okay, entropy is most commonly associated with entropy is most commonly associated with a state of disorder, randomness, or uncertainty. Entropy is most commonly associated with a state of disorder, randomness, or uncertainty. So basically, the universe is getting more and more chaotic over time. And then we have third and the final law. Okay, so let's take this down. The third law of thermodynamics, states that the entropy of a system. The third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. As the temperature approaches absolute zero. So the universe is really big, right? The funny thing is, this distance is 9,000. 900 billion light years. 900 or 9,000 billion light years. That means light takes to go from here to here takes 900 billion years. I'm not exactly sure of the number. I forgot. Anyway, it's pretty big. Okay, and the universe's age is 16 billion, if I remember properly. Okay. So you can see the difference in numbers. We just assume it's 900. I'll tell you the correct number next class. It's Google numbers anyway. So even though it's just 16 billion years, and the fastest thing in the universe is light, somehow this has expanded much faster than light, and it's still expanding. We don't know why. We can't measure sense and energy, but something is pushing everything apart. All the galaxies are going further from each other, and the universe is becoming bigger and bigger. So that is again entropy, right? And since everything is going apart, even the atoms in the object are slightly going apart. And what happens when atoms go apart? The temperature increases, correct? And the atoms become more chaotic. So the third law says that if the temperature goes down, right? The entropy will go down. Basically, since the universe is becoming chaotic, the atoms are this one, what is that, spreading far apart, the temperature is increasing. If we reduce the temperature, obviously the chaos will reduce. That is the third law, but third law, it doesn't directly say that. It says that when the temperature reaches absolute zero is the coldest temperature in the universe. It might surprise you, it's just minus 273 Kelvin. Okay, it's just minus 276 Celsius. It doesn't seem like it's much, but this is the coldest temperature in the universe, and it's not there in the universe. The closest scientists have reached is 272.5. This is the coldest scientists have reached, and it's the coldest in the and they are observed in the universe also. So at this stage, the atoms are in full order. It's like a proper crystal. There is no chaos at all. It's impossible to reach this state because, like I said, it's, here the temperature is hot, here the temperature is cold. This one temperature is absorbed by the cold object. So the entropy increases, right? So this temperature, if it reaches that, the surrounding will make it again hotter. So it is impossible to achieve this temperature. But if you achieve this temperature, that object is a perfect crystal. And there is no chaos at all. That is the third law of thermodynamics. A little bit difficult compared to everything else we did so far, but yeah. Okay, so minus 273 Kelvin, so Celsius, right? And this is equal to 0 Kelvin. 1 degree centigrade, sorry, 1 Kelvin is 273 Celsius. So minus 0 Kelvin. 0 Kelvin is absolute zero. So yeah, I can give you some notes. Okay. Yeah, this one. Okay. There is one nebula. You guys know what's a nebula? Okay. Basically, when a star explodes, there's this huge gas of smoke and dust and gases and everything. Star explosion is huge. Okay. It's not like one small bomb exploding. The light will be there for thousands and millions of years on campus. That's powerful. So a lot of dust and everything is released. That's a nebula. So the coldest temperature scientists have found in space is this one nebula. Okay, it is 5,000 light years away. Huh? So this nebula had reached the temperature of 272.15 degrees centigrade minus. So this is the coldest thing scientists have discovered in the universe. Just one point. It's called the Boomerang Nebula. It's the coldest natural place known in the universe. So yeah, just take a note of this. Okay, the Boomerang Nebula. The Boomerang Nebula, Nebula. Okay. The Boomerang Nebula is the coldest natural place. Known in the universe. Okay, and it is around 5,000 light years away from Earth. It is around 5,000 light years away from Earth, and the temperature measured was around 272.15 degrees centigrade. The temperature measured, it is around 5,000 light years away from Earth, and the temperature measured was around minus 272.15 degrees centigrade, which is approximately equal to 1 Kelvin. Scientists have gone closer than this one. Yeah, I told you, right? So that's not an important point. And absolute zero is just another note. Let's take it down. Absolute zero is 0 Kelvin. Right? And just a simple note: when the temperature reaches when the temperature reaches 0 Kelvin, entropy is the lowest. When the temperature reaches 0 Kelvin, entropy is the lowest. Okay, so we are done with the annoying part. Now we can just go through some simple definitions. All right. So the next child heading is conduction. Just a definition, okay? You all have an idea of what conduction is, right? Just an idea. So I'll just give the definition, you will understand. Conduction is the process by which heat energy conduction is the process by which heat energy is transmitted through conduction is the process by which heat energy is transmitted through direct collision between neighboring atoms, direct collisions between neighboring atoms or molecules, transmitted through direct collisions between neighboring atoms or molecules. I'll repeat. Conduction is the process by which heat energy is transmitted through direct collisions between neighboring atoms or molecules. So again, I'll give you the example I gave yesterday. You have, let's say, and you put ice in it. Ice is colder than water, so it absorbs the heat. And yeah, there is a collision between. Collision is basically a contact. So there is a collision between the atoms, and since the atoms are colliding, there is a transmission of heat. That is conduction. That's all. And conduction differs. This is not a good conductor of heat when compared to iron. Iron conducts heat nicely. Heat and electricity are almost similar. Okay. I mean, like generally, conduct heat, conduct electricity. Generally, there are exceptions. So, iron is a good conductor of heat. Copper is even better conductor of heat than iron. So, yeah, that is conduction. The next term is convection. CONVECTION. Okay, this is simple. Just take it down. When a fluid Sanjana, what's fluid? Yeah. Any liquid or gas or plasma is fluid. Anything that flows. Okay. So when a fluid is heated, when a fluid is heated, it travels away from the source. Sorry, just a correction. When the fluid is heated and travels away from the source, okay, I made a mistake. When a fluid is heated and travels away from the source, comma, when a fluid is heated and travels away from the source, comma, it carries thermal energy along. It carries thermal energy along with it. I'll repeat. When a fluid such as air or liquid, okay, is heated and travels away from the source, it carries thermal energy along with it. This type of heat transfer is convection. This is called convection. So yeah, simple. You heat water vapor. You heat water, it becomes water vapor. It evaporates. It flows up because it's lighter than air, right? And the heat also carries with it. That's all. So when sunlight heats the air at the bottom, the air in the bottom goes up. The cooler air comes down. Correct? So the heat is transferred. The air is traveling up, it's taking the heat along with it. That is convection. Clear? Online class clear? Am I going too fast?
No, it's clear.
Okay, good. Okay, this chapter is almost done. Yeah, the last term is radiation. Radiation. Okay, let's take this down. Thermal radiation or radiation in general. Okay, let's take this down as thermal radiation generates from thermal radiation generates from the emission of electromagnetic waves. Thermal radiation generates from the emission of electromagnetic waves. These waves carry the energy. These waves carry the energy away from the emitting object. Okay, so every single object in the universe emits radiation. Smaller, of course, the amount differs. So the background radiation is, if there's obviously radiation everywhere around us, our body can handle a certain level of radiation. Okay, so every single object releases radiation. That's one more property of every single thing. It's generally because of releasing of electromagnetic waves, like the definition. So basically, let's think of heat and radiation. Heat is basically radiation. That's how it can travel in vacuum from the sun to the earth. Because it's basically waves. Am I clear? It's of course going through different interactions of atoms and all that. But it's generally radiation. So what is that? And the amount of radiation emitted is different for different objects. For example, if you are boiling tea and if you put ice in it, okay, just an example, don't do this. The heat will, or the ice will absorb heat very fast when compared to dropping it in normal tea. So this means that the higher the temperature, more radiation is released. Am I clear? Since the ice absorbs the heat faster, it means that the heat is escaping from this object to the other object. So the radiation is higher when temperature is increased. Just make a note of this point. Okay? The hotter an object, the more it will radiate. In simple terms. The hotter an object, the more it will radiate. And we're done with chapter 7. Fine so far? We start with chapter 8. Okay? I'll give you a break at around 4:10. Okay. The next chapter is wave motion. Yes, chapter 8, wave motion and sound. I forgot the name. Yeah. Okay. So what's a wave? Think of any wave, even the wave in the beach. It's similar. Okay. What is it? Okay, ripples. Yes, you're right. Basically, that's the transfer of disturbance. Like there's a disturbance, and the disturbance is transferred from this part of the water to this part of the water. Same way, even sound is a wave. I'm speaking, the air here is vibrating. This vibration is transferred through all the other air particles around, and it reaches your ear. It's a disturbance that travels through the air. That's a wave, that's all. So, yeah, definition, okay? A wave can be described as a disturbance A wave can be described as a disturbance that travels through a medium, from one location to another. From one location to another. I'll repeat, a wave can be described as a disturbance that travels through a medium from one location to another. Okay, so Sanjana, where does sound travel faster, air or water? Water. Yeah, but it travels faster. I didn't talk about how much you can hear. I'm telling how fast it travels. It travels faster. Your ears are meant to listen in the air. That's why you can't. Your ears are meant to listen in the air, not in the water. It travels faster than water in wood. I told you, your ears are designed to listen in the air. If you go in the water, how will you hear? It is meant to, what is it? It reacts according to the change in the vibration of the air, not of the water. Then water, it tries to do its job, but in this more dense, you hear it less. Okay. So there are many types of waves. Okay. So now we are just concentrating on mechanical waves. They are not given much definition and all in the material. Okay, so we won't go through it. There's no need. So just take down the types of mechanical waves. Types of mechanical waves. First one is transverse waves. Transverse waves. Okay. When you think of a wave, what do you picture? If someone says wave, what do you imagine? Let's say a picture. Okay, think of a science book. What picture would they give? Okay. Yes. Is that transfer? Generally, light, water. These are examples of transverse waves. In the definition, they are given like this is 90 degrees. Getting me? When the particles are at right angle of perpendicular to the motion of energy. And okay. So yeah, waves which travel like this are transverse waves. And there is another type of wave. It's somewhat like this. It's a little complex to imagine. I can't just explain the diagram. But basically, like imagine some particles are there. The wave is like this is a particle wave. It moves here and comes back. It just goes like this, like this. Another maybe like this, like this. So that thing is in motion. But the particles are not moving friendly, just going front and back and back. So this is the other type of wave called longitudinal wave. Longitudinal, I have to pronounce it. Longitudinal wave. Okay, so this is a little tough to explain. I did my best. So, like you can, one more way to imagine is, okay, just think of a boat floating in the ocean. When the wave goes up and down, don't imagine like a tsunami or something, some small wave up and down. And the boat will remain in the same position, right? Or sometimes it might go like this and come back, go like this, come back. That is, you can imagine that as longitudinal. Generally, sound waves are like that. So you have, I'm talking over here. This sound wave, this sound wave, from here it goes like this. This particle doesn't travel. It hits this particle and travels. That is longitudinal. So I gave you multiple images. I hope you guys get it. Okay. So yeah, take down the definition for transverse waves. When the movement of particles is at right angle, when the movement of particles is at right angles, ANGLES, when the movement of particles is at right angles, or perpendicular to the motion of energy, or perpendicular to the motion of energy, the type of wave is known as transverse wave. I'll repeat, when the movement of particles is at a right angle or perpendicular to the motion of energy, then this type of wave is known as transverse wave. Okay. Examples for transverse waves are water and light. Water when it's waves in the ocean, or maybe even river flowing, and light. So when we picture light, just think light goes like this. It does, but the wave of light is like this. Okay, it's a little rough, right? And no wave. Basically, this is equal to, okay. So the definition says that the angle between the flow of energy, light is of energy, right? This is the flow of energy, and the waves are traveling perpendicular. That's all. You can take on a diagram. It's perpendicular. So longitudinal wave, there is no proper diagram. Okay, anyway. Second one is longitudinal wave. Online class, can you guys see the board?
Yes, sir.
Yes.
Okay, okay. Second type. You're clear with the what was that? Transverse waves, right?
Yes, sir.
Okay,
Yeah.
good. All right. So yeah, I'll give you the definition of longitudinal waves. In this type of waves, it's an explanation rather than a definition. In this type of wave, the motion of particles is in the same direction. The movements of particles are in the same direction or are parallel to the motion of energy, or are parallel to the motion of energy. So this is the let's say the big arrow is the direction of energy, and the small arrow is the motion of the particle. The particles go like this, like this. Just take the form, not an exact diagram, but yeah. This is the direction of the energy, the big arrow, and if it is a particle, it goes like this, comes back. It moves that way. It is parallel to the flow of energy. one is perpendicular to the floor. An example for this is sound. Example for longitudinal wave is sound. Okay, the next slide is sound. See this, what is sound? Okay. Take down the definition. I saw it. Okay, maybe. It's okay. So, yeah, take down the definition of the word sound. Sound is energy that travels in wave form Sound is energy that travels in wave form through air, water, or other substances. Easy? I repeat, sound is energy that travels in wave form through air, water, and other substances. The next word is echo. I'm not going to explain too much. You all know all these words. The next word is echo. 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 Echo is, take this down. Echo is a reflection of sound Echo is a reflection of sound that arrives. Echo is a reflection of sound that arrives at the listener. With a delay. That arrives at the listener with a delay after the direct sound. Echo is a reflection of sound that arrives at the listener with a delay after the direct sound. A wall, right? Like I said, sound is like there are particles everywhere, atoms. So this particle transfers energy like when it hits the wall, the atoms of the wall are very tightly packed. So it can't just, the atom won't just move. So since the atom is staying here, the atom, the sound is hit back. Slight of the energy is absorbed. That's why the echo sound will be slightly lower in volume. And from there, once it bounces back, again the energy is transferred and comes back to the listener. I think sound is kind of slow. It comes in a delay. What's the speed of sound? 300 meters per second. Okay, so the speed of sound is 300 meters per second. Approximately. Okay. The next word is reverberation. R-E, I'll write here. Have you heard the word reverb before? None of you are listening to a stage. Okay, there's a setting called reverb. Okay, when you're singing karaoke or whatever, like you're a singer, even instruments can use. So basically, after I talk, you can hear the sound again, like after like when singers sing, their voice slightly echoes. That setting is called reverb. That's basically the definition. So it's just like after I talk, just imagine usually that what is that? There is artificial reverberation. Yeah, musicians have put in that amplifier. Natural reverberation will occur in certain rooms, usually dorm rooms or something like that. Once you talk, you can hear the reflection, the echo, right? But it's not just an echo. It's like you can hear it multiple times, correct? And it's like you can hear the voice and it slowly fades away. That is reverberation. Getting me? Okay. So just take down. Reverberation is the phenomenon of reverberation is the phenomenon of persistence of sound. Persistence of sound meaning the sound being there. Are you getting me? Like sound being present. The persistence of sound after it has been stopped. The presence of sound, the persistence of sound, my bad. The persistence of sound after it has been stopped. After it has been stopped as a result of multiple reflections after it has been stopped as a result of multiple reflections within a closed surface. Within a closed surface. I'll repeat, reverberation is the phenomenon of persistence of sound after it has been stopped as a result of multiple reflections from surfaces, multiple reflections within a closed surface. As a result of multiple reflections within a closed surface. Done? Okay. The next heading is infrasound. Any idea? Basically, sound which is so low you can't hear. Sound with frequency very low. You know what low pitch is? So human ear can hear only a certain degree, certain range. So below that is called infrasound. So let's take this down. Sound waves, infrasound are sound waves. Infrasound are sound waves with a frequency below the lower limit. Infrasound are sound waves with a frequency below the lower limit of audibility. Below the lower limit of audibility. These are also called infrasonic waves. They are also called infrasonic waves. Okay, next one is audible sound or audible waves. One second. Second one is audible waves or audible sound. Okay, one point under infrasound, the range is between 0 hertz to 20. Yes. This range is infrasound. 0 meaning no sound, and this is very low. You know what frequency, right? Waves are there, right? Some waves are like this, some waves are like this, correct? Some are like this. That is wave with different frequency. Lower frequency, higher. So yeah, this is the infrasound wave range. The next one is audible waves. Take this down. Sound waves. If audible waves are sound waves which are audible. It is self-explanatory. Sound waves which are audible. Audible waves are sound waves which are audible. And the frequency is 20 hertz to 20,000. This is the audible. And what's the third one? Any guesses? One is infrasound, second one is audible range, and sound waves which are high frequency are. Any guesses? You definitely have heard the term ultrasonic. The third form is ultrasonic waves. Ultrasonic waves. Ultrasonic waves are sound waves. Ultrasonic waves are sound waves with a frequency. Ultrasonic waves are sound waves with a frequency above the limit of audibility. Above the limit of audibility. And what's the range? Range and above. So the frequency is 20,000 hertz and above. Your eardrums will burst. So above that frequency, your eardrums will burst. 20,000 hertz. Nice. But also hearing also it depends on other factors also. Not everyone is confined to this 20,000. Some people can hear slightly more than others. Of course, there is age, genetics, diseases, how much you listen to music with loud volume, all that can. older people can't hear high frequency when compared to younger people. Generally, at age 15, people start losing their hearing from 15. Okay. The next side heading is sound intensity. Sound intensity, also known as acoustic intensity. Also known as acoustic intensity. Yeah, take this down. The intensity is sound intensity is the amount of energy flowing per unit time, the amount of energy flowing per unit time through a unit area, the amount of energy flowing per unit time through a unit area that is perpendicular to the direction that is perpendicular to the direction in which sound waves are traveling. So, what is it called in other terms? Like not called. What did you understand? It is the intensity of sound. Are you getting me? Basically, like it is how much energy is flowing. The amount of energy is the intensity. Basically, volume. Lower the volume, lower the intensity. Increase the volume, more energy is flowing. Higher intensity. That's it. So the SI unit for this is watt per meter square. Since you are new, there are a lot of SI unit is watt per meter square. Oh yeah, it's 16:12. We'll take a 5 minutes break. I'll see you at 4:17. It's time to get back to class. Loudness. Okay. So, okay. Loudness depends on, yeah, high rating is loudness. So loudness depends on the intensity of sound. Right? I told you, right? Higher the intensity, higher the volume. The previous one. The intensity of sound. Right? Okay. The next word is pitch. Pitch. The sensation of a frequency. The sensation of a frequency is referred to as the sensation of a frequency is referred to as the pitch of a sound. Right? So basically, the sound waves have a frequency. When a particular sound wave of a frequency of sound wave hits our ears, we hear the sound. The one with the higher frequency will give a higher pitch, higher frequency like this. And the one with the lower frequency will give a lower sound. That's all. So yeah, let's take down a high pitch sound. A high pitch sound corresponds to a high pitch sound corresponds to a high frequency sound wave corresponds to a high frequency sound wave. A high pitch sound corresponds to a high frequency sound wave and vice versa. Yeah, or vice versa is French for opposite. Like basically, instead of saying again a low pitch sound corresponds when they say vice versa. You haven't heard the word before? Okay, and vice versa. Then next one is shock wave. Shock wave. Okay, have you watched Dragon Ball? Okay, so when Goku goes past, you can see like the air moving around. That is shock wave. So for example, the people imagine a rocket is traveling, and when a rocket is traveling or a missile, there's a lot of fluctuation in the air. So all the fluctuation of the sound that is created when an object moves past is a shock wave. It can even happen from an explosion. When an object explodes, full layer comes rushing out. Sound wave which comes out very fast. That's a shock wave. Yes? Okay. So take this down. A shock wave is a shock wave is a type of sound wave. A shock wave is a type of sound wave created by an object moving through the medium. A shock wave is a type of sound wave created by an object moving through a medium at a speed faster than the natural speed faster than the natural speed of sound in that medium. Here, when an object moves faster than sound happens. Jet play, all that jet plane, rockets, missiles, or Dragon Ball Z. You watch Dragon Ball Z? Watch it. It's good. It's a anime. You know what's an anime? Yeah, animation. Yeah, yeah. It's very old. It's amazing. It's actually Japanese, but yeah, it's very famous. How could it? Everyone knows Dragon Ball Z. Every single person. So it used to come in cartoon. It used to come in cartoon. Anyway, yeah, it's good. So in that, like, they draw that, so you can like properly imagine how a shockwave is that. Okay. Next one is refraction of sound. Refraction of sound. You know what's refraction? Yashwant? No? Passing through a medium with change direction. So this sound passing through a medium. I'll give the definition. Okay, so it's just like light. Okay. So you have the sea, and you're in a submarine. The sound is coming from here. I think this angle is not that good. Okay, this angle. And hits the water. The sound tends to change direction a little bit. That is refraction. The same thing is light. Even light that enters tends to change a little bit. The angle is obviously not this much, but yeah, this is an example. It's slight change. This is refraction of sound. So yeah, take this down. Anyone take down this? A change in, or refraction of sound, a change in the direction of waves, a change in the direction of waves as they pass from, a change in the direction of waves as they pass from one medium to another, as they pass from one medium to another. So yeah, when refraction occurs, it's not in the direction that changes, even the speed changes also. Because I told you, sound travels faster in water, so you can notice the change in speed. That's one. And you can just draw a simple diagram. the sound wave. This is the air, and this is water. You don't have to. I don't know why it is. Okay, so for the next one, I just need to connect my laptop to the internet. Give me 1 minute. Just yeah, take down this. The next side thing is a beat. Beat. B E E. Pretty sure you all know what a beat is. But we are not talking about this beat. Here, this is a different kind of beat. I mean, it involves sound only, but so yeah, take down this definition. The periodic vibration in the intensity of sound, the periodic vibration in the intensity of sound caused by the combination of two sound waves of slightly different frequency. The periodic vibrations in the intensity of sound caused by the combination of two sound waves of slightly different frequency. So, okay, I told you intensity of frequency. This is high frequency, this is low frequency. Now, just imagine you have two sound waves. One is in this, and the other one is slightly less. This was only that it is slightly less or slightly more. The second one will say slightly less. Okay, we take it as slightly more. Anyway, it goes a little like this, and there's a point over here where it meets, right? And again it continues like that, and again somewhere here it will meet, right? So because of this nature, even though the frequency is like this one might be like, this one might be slightly lower, but when those two combine, for some reason it goes like like that. There's a bend in this one. It's like sound stops at this point. That is the beat. It's a little difficult to understand, so this is website. Online class, just tell me if you guys can hear this. So this is 440 hertz. Okay. So I'll make this. This is 436 hertz now. We'll make it 435 hertz. I'll stop the sound. Online class, can you hear the sound?
Yes, yes.
Okay. So that sound was 435 hertz. Okay. I'll play it again. This is 435. You can hear that as well. Okay. So now I'll play 440 hertz. It sounds similar, very less change. Okay, now 440 hertz is playing. right now. 440 hertz is playing. Now listen when I play 435. Tun, 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 tun. Even though it's playing continuously, it sounds like this when it interferes. So this is a beat. If I stop one, it again goes back to continuously. Did you guys get that online class?
Yes.
Yes, sir.
So two waves cause this and they interact, which causes an interference which gives rise to a beat. Okay, two waves interact, which causes an interference resulting to a beat. The next one is Doppler effect. Doppler. You all probably know this. The ambulance example. When ambulance is coming, you can hear it loud and it's far away. That one now. Okay. Doppler effect refers to, take this down. Doppler effect refers to the change in Doppler effect refers to the change in wave frequency during the relative motion. Doppler effect refers to the change in wave frequency during the relative motion between a wave source and its observer. A classic example everyone uses ambulance. Okay. So when the ambulance is moving and you are standing over here, you can hear the frequency in a higher pitch. But as soon as this ambulance passes you, the frequency starts getting lower. That is the Doppler effect. Because the object is moving, there is a change in the frequency of sound with respect to the one observing it. When the source of the sound is moving. So the ambulance will be like, it goes lower. That is Doppler effect. So in the slide example, when an ambulance passes by, something like that, yeah. When the ambulance passes by, the frequency lowers. Okay. Next one is sonar. Sonar. What is sonar? Submarines? To what? They use it by traveling, but what exactly? Yes. And they know there's an object is present. Okay. So the maybe the yeah. For sonar, one example is submarine. So you have a submarine. It sends out sound waves. Okay. It sends sound waves like this. So if there's an object here, for example, here, there's a dead body in the ocean. It just hits the sound hits the object and comes back. So when the sound waves come back, he is a submarine. And submarine knows that with calculation, let's say this is 300 meters away. So sound takes 1 second to go here and 1 second to come back. So with that, they'll measure and they'll know how far the object is. That is sonar. Another best example is bats. Bats don't have, they have a good eye. That's a myth. No, that's a myth. They have eyes, they can see. But they can't see that well in the dark. So they use sonar. So bats release this sound with an insect here. Sound is the insect and it comes back. That's when the bat knows there's an insect. And the distance won't be much, few meters. So the sound is like almost immediate. So that is sonar. So yeah, take this down. Sonar is a technique that uses sound Sonar is a technique that uses sound to detect objects or navigate. To detect objects or navigate. It is usually used underwater. Okay, so the uses of sonar. There are 5 uses. Take this down. Okay. Special sonars are used in ships and submarines for underwater communication. Okay. Second use, it is used in medical imaging. IMAGING. Imaging means taking a picture, like getting a picture, using sound. Medical imaging for the detection of cancer cells, foreign objects, or any other problems in the body. Used it is used in medical imaging for the detection of cancer cells, foreign objects, and any other problems in the body. This procedure is known as sonogram. This procedure or this method is known as sonogram. Sonogram. Right? The third use is it is used for detection of enemy vessels. It is used for the detection of enemy vessels. 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 Vessels can be anything: ship, submarine, enemy vessels, and torpedo. No, what's a torpedo? Torpedo. 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 Missile. You can just write missile if you want. Torpedo is a common word. So it is used for the detection of enemy vessels and torpedoes. Torpedos by the military. It is used for the detection of enemy vessels and torpedoes by the military. Torpedoes means missiles. Okay. Fourth use is it is used for fishing. Not in India. We have enough fish also. We don't need to use this. US and all that, when they go deep into the ocean to fish for fishes which are like way under the ocean, they use sonar to detect the fish and then they drop the net 100, 200, 400 meters down from that distance. So then they drop this one and then they catch it. And the fifth use, of course there are more uses than this, I'll just give it 5. It is used for measuring. The depth. It is used for measuring the depth of particular parts. It is used for measuring the depth of particular parts of the ocean. It is used for measuring the depth of particular parts of the ocean. Okay. The next side heading is here. Here. Yeah. What's the year? That? And what is it used for? And yeah, hearing, and it also helps in maintaining balance. The ear helps in, not just in hearing, there's this certain thing it helps in maintaining balance. Understand? Some people get travel sickness because that part goes crazy. It goes up and down. See, it's like motion sickness is like you're in a bus or even if you're watching a movie, something moving. Your eye is telling that you're moving, but your body can't feel that you're moving. That's why the brain gets confused. Body meaning your ears. Your ears gives that signal. There's this part which helps in maintaining balance, and it detects like if it's going this way, it'll detect and it'll give the signal that you're going this way. So because there's a fluctuation in both the signals, you get motion. So the ear is just not just used for, it's not in all animals, okay? So only usually in mammals, that's the second function, but it's there for also maintaining balance. And yeah, so just take this down. The ear is the ear is the organ. The ear is the organ of hearing. The ear is the organ of hearing. In mammals, it is also used for maintaining balance. In mammals, it is also used in maintaining balance. So there are three parts of the ear. Any guesses? Uh-huh. We are not going that much. They are just given outer ear, middle ear, and inner ear. Okay, so there are three parts of the ear. Outer ear, the middle ear, and the inner ear. Outer ear, middle ear, and inner ear. Okay, so thank you, class. The class is done. You all can. I'll just talk to sir and then tell you if you can log out. There's no class. I'll just tell you. Okay, guys, you can log off. Thank you.
Thank
There's no
you.
class.
Thank you, sir.
So welcome. I didn't think we finished the chapter. Went by fast. Yeah, really happening. What are the things?